start
You
吗
remember?
3。
不行，我这杯子
Okay, so we
你录啥地方？拿你
we discussed question 1, 2, 3 last tutorial, but I
你确定你能
have
录好
also
不？
gone through
还有
this
这边
slides.
儿，这边
So
儿
these are the
把这杯子往上，
GPIO.
你把那绿的是谁的？把那绿的
Okay,
拿
these
过来。
are the GPIO registers
拿过来吧，拿过来。
for you to set up your pins. Okay, to set up your pins. For example, FIODIR helps you to set up the pin, the GPIO pin to either input or output. Right? That's why it's called
你们
direction.
你们真的是拿个杯子都里面都没水。
Right? Still remember? And you have the FIO mask register. Okay, so if you mask off some pins, you cannot read or write from the pins. Okay, and you have FIO pin. Okay, maybe this slice. Remember the FIO DIR, if you write 1 here, means you want this pin to be output. If you write 0, means you want this pin to be input. So the pin is actually, for example, for my case, called 0 pin 7, because here I will put FIO 0.
不准慌。
FIO 0 DIR. If I write 1 at bit 7 location, means I want my port 0 pin 7 to be an output. Right? So if I write 0 here, I want it to be input. Okay? And FIO set and FIO clear allows you to control an output pin to output either 1 or 0. Right? So if you want your pin, let's say P2.10, okay, let's say this one is an output. And if you write FIO2 set at location 10, if you write 1 here, means you are going to output 1 from this pin. Okay, if you write 0 to this register, it doesn't take any effect because this is a set register. Okay, if you want to output 0 from this pin, you go to the corresponding clear register and write 1 here. Means you want to clear the pin. Clear means you want to output 0 from the pin. Okay? And you have another register FIOX pin. Okay, if your particular pin is an output, this is a register that you can directly output 1 or 0 by putting 1 or 0 here. But let's say your pin is an input. If your pin is an input, basically you are going to read from this register instead of write to it. Okay? You read this register, look at this corresponding position, see whether it's 1 or 0. This means the bit you are receiving from this pin. Okay, since it's an input pin. Okay, and finally you have this FIO mask register. If you write 1 here, means you are not going to be able to write or read or set or clear that particular pin. Okay, you mask the pin off. You cannot control the pin anymore. Okay, so these are the registers for GPIO. Okay, so let's look at the question 4. Okay, so question 4 is asking you, is there any difference between this line and this line? Okay, so the first one, LPC GPIO2 FIO mask equals to this value. Okay, this means, okay, the first line basically means you want your FIO2 mask to be holding this value FFFF0000. Okay, this is basically, this one. Okay, you are giving a value to this register. Okay, so basically your register becomes this value. So what does it mean? Once you set your FiO2 mask register like this, what did you do? Remember, if you write 1 to the mask register, what will happen? You are no longer be able to control the pins. Okay? So you see, for this case, F means 1, right? 1111, right? So this is in hexadecimal. So this is talking about the entire port 2, right? Since it's FiO2. So for port 2, you have totally how many pins? 32 pins, okay? 32 pins. And you basically mask off half of them. Okay? Which means from pin, okay, this is 16 up to pin 31, you are no longer be able to control them, or to read, to write, to set, to clear. You cannot do that anymore after this line. Okay? So this is the first line. Then how about the second line? FiO underscore set mask bracket these 3 values. Can you see that this is a function? Okay, this is a C function actually given by the library. So to understand what's happening here, you need to look at the code of this function. Okay, so this is the code. You see, you have FiO set mask. Okay, it returns nothing since it's void, and it requires 3 parameters. First one, port number, bit value, mask value. Okay. By the way, in your lab, when you see any things in the library, there is a brief explanation in front of it. So here, you see the comments here, this is an explanation of this function. Okay, so you see this function is set mask value for bits in FiO output. And if you don't understand these parameters, read here. Okay, you see port number in range from 0 to 4 because you have 5 ports for your LPC1769. Okay, and you have bit value that contains all bits to set in range of 0 all the way to FFFF. Why this value? Because you have 32 pins. Okay, so you can see that the type of the second parameter is an unsigned integer 32-bit value. Okay, and lastly, you have mask value. Okay, mask value contains state value for each bit 0 or 1. So basically here, you can only put 0 or 1. Okay. Then let's see how this one works. If we have these parameters. Okay, so your port number is 2, right? The second, okay, let me write it here. So the port number is 2. The bit value is FFFF0000. The last mask value is 1. So let's look at the code. Okay, so firstly, basically it's defining a pointer, okay, pointing to the port. And look at here. Okay, if this one is null, means you have something pointed to, okay? And if else loop here, based on your mask value. What is the mask value now? 1. So you go here, right? So you see what's happening here? So this one is a pointer pointing to your mask, your mask register, okay? So this basically is your original mask register, okay? before you do anything, there are values in your mask register. Okay, so this one, FiO2 mask, you have something inside it already. Okay, although we don't know the values. Okay, and what are we doing here? This one means what? OR, right? Bitwise OR, okay? Bitwise OR. Okay, means you are going to do OR condition bit by bit. Okay, you are doing OR with which value? Your bit value. This value.
Yeah.
Okay, so you are basically OR this one with this one, right? Or this one with F 0 0 0 0. What will you get? What should be here? What should be here? F, right? Because anything all with 1, you will get 1. Okay, so here you will get F. The other place, X. Okay? So then this value, can you see that? This will be updated. This will be the value put back to the mask register, right? This one means this one equals to this or this, right? So in short, it's written in this way. So basically, this is your old mask register values. This is your new values. Now, can you see the difference? You see what's the difference of these two lines? What's the consequence? So this will be the result for the first line. The second one, your result will be F, X. Okay, so basically the first line close up the upper half of the pod. Means you cannot control them anymore. You cannot read, you cannot write, you cannot set, you cannot clear. But it's open the lower half. You can do for the rest of the 16 pins. But for this one, you mask off the higher half, but the lower half, you remain no change. Okay? Maybe previously already some pins here are already masked off. You know, here may not be zeros originally. Okay? So by calling this function, basically you mask off the position that you indicated by the bit value. Can you see that? You mask off the upper half. You mask off the upper half, you remain the rest of the place no change. Okay? So you see the difference now, right? Any questions? So this is the answer. Okay, so for the first line you get this result, for second line you get this. Okay, values here no change. So for the lower half of the pod, if some pins already masked off, you didn't change them, you didn't reopen them. Okay. Then let's see question 5. You will get better understanding of the other registers. Okay. So an LPC 1769 system is reset before the following lines in the C program are executed. So the question is basically asking you what will happen after each of these lines. Okay? So the first one, this is quite similar with the previous one, right? So what are we doing here? What are we doing? The register we are giving value to is FiO dir. right? So we want our FIO DIR, basically FIO2 DIR equals to this value. So what does it mean? What is FIO DIR? Input or output, right? It's direction. See here, the first one is the direction register. If you write 1, you set the pins as output. If you write 0, you set pins as input. So here, what am I doing? I'm setting my entire port 2 to be output. Okay? And then A equals to GPIO read value 2. So this is a function again given by the library. Okay? It requires only one parameter, which is the port number. And it will return you the entire port. Whatever received from this entire port. You get my idea? So basically you have your LPC. Let me draw it here. Your LPC. You have your port 2. Okay, you have port 2. This one is port 2, totally this amount of pins. Okay? And line 1 is to set all of this to be output. Okay? You are setting all of them to the output, so they are sending out data. Okay? And then GPIO read value means your LPC wants to know what data are sending out. He wants to know the status of these pins. What are receiving or what are sending. Okay? So what will you get from here? What will be the A value? What are you sending out now at this moment? There's one keyword in the question saying that your system is reset before you executing all these lines. Okay? Once it's reset, basically all the pins are sending out 0. Okay? All the pins are sending out 0. Okay, that makes sense, right? Because let's say if you want to turn on your machine and your machine is connecting to one equipment, you don't want, like, when you turn on, you give a large current and you just destroy that machine, right? So to be safe, when you turn on, you better output nothing, or you better output no current. Right? So at the beginning, all your pins, once it's reset, all the pins are sending out 0. Okay? So what you get here is your A is basically equals to 0, 0, 0, 0, 0, 0, 0, 0. Okay, totally 32 bit. Okay? And then second, FIO set mask to FIO001. Okay, you saw this just now, right? What are we doing here? You want to mask off your upper half of the port, remain the lower half, no change. Right? And then what will be B's value? B, again, you are reading what's happening for your pins. Okay, so what is B's value now? No, this one is asking you what are the pins value. What are you sending out from the pins? After step 1, you are sending out zeros. After you do this, what are you sending out? You didn't do anything, right? You didn't modify any pins, you didn't change any output, so it's still 0. Okay? You are not sending anything, you are not editing anything. Okay? And then next one. LPC GPIO2 FIO pin equals to AAA. Which register we are modifying?
Pin.
FIO pin, right? What is FIO pin? What is FIO pin? FIO pin is either you can modify the output you want to send out if the pin is an output, or you can get the status of the pin if the pin is an input, right? So for our case, what are our pins? Output or input? Output, right? So if I try to write A to this one, what are we doing? A means 1 0, right? So you have 1 0 1 0 1 0 1 0 1 0 1 0 and so on 1 0 1 0. Okay? So if you just look at this one single line, basically you try to output 0 from pin 0, output 1 from my pin 1, output 0 from my pin 3, pin 2, output 1 from my pin 3, and so on, right? This is the output I want to send out from my port 2, right? That's it if you just look at this line. But what have been done previously? Can you see that you have masked off the upper half? So in future you are not able to do anything for the upper half, right? So if you erase upper half, what are we actually outputting now?
0 0 0 0 1 0.
A.
What are we outputting?
0 0.
Let me see the question.
What's the value A, B, C, D, E, F, G?
Okay, so you have masked off the upper half. You cannot modify them, right? Then what do you get here? C equals to
0
Upper half.
0 0 0 0. That is C. But that's not correct. You have one more thing that you need to check, okay? This is like what we have done in the software side, right? We want to mask off the upper half, right? But you also need to consider your your actual hardware. What's the condition of the hardware? So this table is your LPC 1769 user manual. Okay? This table is for your port 2. Can you see that? Here you have pin 2.0, okay? Pin 0, pin 1, pin 2, pin 3, pin 4. All this up to pin 13, you can program them to different functions. But from pin 14 onwards, can you see here? It's called reserved. Means we as a user of LPC 1769, we don't have the permission to use them. Okay, they are used for itself, maybe used for some other connections. It's reserved that we cannot modify, we cannot touch, we cannot use. Okay, so this is like the original mask of your port that even though you don't do anything, these pins cannot be used, cannot be programmed by us. Okay, so you can only use up to 13. Okay, so once you know this, what do you get for your C? As I mentioned, you don't have only this mask, you have another mask up to, from the upper half up to pin 13, right? Pin 14 basically. Pin 13 is the last one you can use. So what do we have here? This one is 1010, right? So you are outputting 0 up to pin 3, right? This one up to pin 7. This one up to pin 11. And this one, 1010, here should be 12, pin 12, pin 13, pin 14, pin 15. As I said, these two, you cannot do anything. Okay? So what should be the A value? What should be the C value? 2AAA. Can you see that? So here you get 2AAA because further than that you cannot use them. You cannot modify them. Get it? So what I'm saying here is this is the actual condition for your hardware. You need to always refer to this if you want to use it. Okay? So you need to check what actual resources you have. You don't have that pin, you cannot do anything. Okay, then that's the answer for C. Next, what are we doing? GPIO set direction 2, 1, less 16, 1. Okay, maybe let me write it here. I have this one. Okay, we are here. So C is 00002 AAA. Okay? And this one. Again, this is another function given by the library. For those who have your lab already, you know that this is to set the direction of your pins. Right? So, which pins are we setting? Port 2, pin 16. Okay, port 2, pin 16, we want it to be output. Can we do that? Cannot, right? Remember, we cannot use any pin beyond pin 13. So basically, this line is not going to take any effect. Okay? You cannot do that. I mean, you won't show any error here, but in hardware set, it doesn't do anything over there. Okay? So what will be your D value?
C value.
No change. Okay? And then next. What are we doing here? You are setting port 2 pin 10 as output. Can you do that? You can, right? Then what's the effect of E? Did we modify any output? Did we change our output? No, okay? So the set direction, okay, set direction or you set the mask, all these are settings. You are not changing any output, okay? So basically this one can take an effect, Okay, it's working on your hardware, but you are not changing anything. So E is still equals to C. Okay? Then F, sorry, this one.
Set that pin.
GPIO set value to 1 less 16. Okay, again, this is a function given by the library. Okay, this one is basically trying to set port 2 pin 16 to output 1 because it's set. Okay, it's set value. Okay, so look at your current output. What will be the value for F?
Set value.
You need to always remember that here, okay, 1 0, okay, then 1 0 1 0, 1 0 1 0, 1 0 1 0. Okay, this is pin 0, pin 3, 4, 7, 8, 11, 12, 13. Okay, and for this one,
Pin.
you can you do that?
No.
You cannot, right? Remember, they are not programmable by us. Okay, so this one cannot take the effect. Okay, so your F will be still this value. Okay, and the next one. Okay, this one also doesn't work. And the next one, you want to set port 2 pin 10 to output 1. What was the output from port 2 pin 10? Where is 10?
0.
Here, right? So basically, this one can work, right? And you are changing this one to 1. What do you get? G is okay. Now it becomes 1 0 1 1 1 0 1 0 1 0 1 0 1 0. This is your output now. Okay. Then next one. Cannot take effect, right? You want to clear the output. Basically, you want to. This one is to output 0 from certain pin. Okay. So this one doesn't take any effect. Your result will be still like that. Okay. Then next one. You want to clear the pin 10. Okay, and then this one becomes 0 again. Okay, so the last one, I equals to, you will go back to your previous value to A. Okay? So the key thing here is, remember, you mask off the upper half, and you also have the, system has its own mask. Okay? So this is the answer, okay? Then last question. A computer engineer connects 2 active low push buttons to port 2 pin 0 and port 2 pin 4. Okay, so it's an active low push button. What is active low, basically? What is active low? Active low, just by name, just when it's active, it will be low. It will be 0. Okay? So, like our SW3, SW4, if you have had your lab already, you have a pull-up circuit, remember? And you have a push button here. And if you press your button, okay, so basically you are observing from here. Okay, you are observing all your LPC is here. Okay, your LPC keeps sensing the voltage level at this point. So if the push button is not pressed, you will get 1, right? You will sense 1 at this side, right? But when the button is pressed, or when we say the device is activated, you will sense 0, which is low. So this is called active low. Okay? When it's active, you will get low. So question is saying that you are connecting 2 push buttons to P2.0 and P2.4 to trigger general purpose input-output interrupts. Okay? You all know what interrupt is? Okay, interrupt is like, the opposite word for interrupt is regular, Let's say if I'm writing some stuff in my office, and then I go for lunch at 12 p.m. and then I go back work, and then at 5 p.m. I go to eat again. This is my routine. So this is my regular actions, right? But let's say at a certain moment, student come knock the door and ask questions. This is called interrupt because it's not planned, right? And if the things coming in has a higher priority than my regular stuff, right? Student asking questions, higher priority, I will answer that first. So you will pause your regular event and do that interrupt first. You finish that, you go back to your regular routine. Okay, so that's called interrupt. So interrupt means it will pause your regular routine and it has higher priority comparing to your regular routine. Okay, so this is called interrupt. So the desired system behavior is that the message button pressed will appear once on the console whenever any of the push button is pressed. Okay, so you have 2 push buttons. Any of them pressed, you should print button pressed. Okay, so this engineer wrote this code. Okay, GPIO interrupt handler printf button pressed. But when he compile and run the program, he doesn't see the response on the console when he presses the push buttons. Explain what he could have done wrong. So then write a correct program. Okay, so this is talking about how the LPC 1769 is handling interrupt. Okay, so to handle the interrupt, there is a system. Okay, there's a controller we call nested vector interrupt controller, or we call NVIC. This is a system that handling all the interrupt events for our processor. Okay, and the GPIO interrupt is one type of the interrupt. Okay, you have other types of interrupt. So, but this one, NVIC, is a manager to control all the interrupts. Okay, so if you look at this block diagram, okay, so basically your interrupt, your LPC 1769, it can control different devices. For example, your push buttons, they are GPIO devices, right? Simple ones. And you also have I2C devices, okay? For example, your 7-segment, okay? And your temperature sensor, your light sensor, okay? They are I2C devices. And some of them are SPI devices, okay? So basically your NVIC is handling all of them, okay? Not only GPIO devices. So you see, let's say you have a GPIO, okay? So this one is you can imagine they are the interface. Okay, here is something, your LPC 1769, the small chip over there, okay? And these are the devices, like the devices on your baseboard. Okay, so this one I2C2 or I2C1, you also have I2C1 and ENT3, GPIO, ENT1. You can imagine they are the interface of your LPC, and they are connected to the external devices. Okay, and for regular routine, okay, for example, your light sensor is sensing the light intensity. It will give information here, okay, and normally it will transmit to, send the data to the ARM processor through this way, okay, regularly, okay. But let's say if you did some setting telling your LPC that, okay, this device is very important to me. Whenever I receive data from here, I should deal with the data first. I should immediately process the data. Okay, if you did the settings here, then once the data coming from light sensor here, it will go in this way. Okay, your interrupt will be, okay, so basically this is like a notification to your processor telling that, oh, something is received from your higher priority device. Okay, and then it will process the data of light sensor first. Okay, so you see NVIC here is handling all these notifications. Okay, can be from I2C, can be from here, can be from GPIO, okay, can be from ENT1, okay. So let's say you have multiple interrupts. So here you should tell NVIC which one is the highest priority, which one is a little bit lower, which one is a little bit lower, which one is basically not an interrupt at all. Okay, so this is how it works. So if you look at here, for this question, we are talking about GPIO interrupts. So you can imagine your GPIO here, which is this interface. There are actually two push buttons here. You can imagine something like this. Okay, so there are two push buttons. They are using GPIO interface. And if any of this is pressed, you want to notify your NVIC that there is a GPIO interrupt. Okay, so this is the idea of the question. So I basically, so if you look at this carefully, okay, if you look at this carefully, you see this interrupt going to a NVIC. Can you see that there's an OR gate here? Okay, and there's another input to your OR gate, which is another GPIO, right? So basically here I basically summarize all the GPIO devices. And there's another OR gate here. Is coming from the ENT3. And then once the two merge together, for NVIC, whatever data received from here, it actually considers this interrupt as ENT3 interrupt. Can you see that? So for NVIC, basically it cannot differentiate whether the interrupt coming from here is from ENT3 or GPIO0 or GPIO2. Okay, so if I redraw, okay, I draw this one, easier to see. So this is your NVIC. We can say that our GPIO interrupt is actually share this interface with ENT3. Okay, so whenever you get interrupt signal from GPIO devices, for NVIC, it considers it as an ENT3 interrupt. Okay, so this is the idea. This is due to the design of the processor. Get the idea? Then something else you need to know is GPIO interrupt registers. Similar to your normal GPIO peripheral, just now we discussed, when you are handling the GPIO interrupts, we are using registers to handle it. Okay, so you have NT-ENR, NT-ENF, status R, status F, clear status. So let me explain this. So I draw it here. Okay, so this is a register ENR, ENF, status F, status R, clear. Okay, I didn't draw the status. So what will happen is these two registers, they are used for write. Okay, write only means you need to write 1 or 0 to these two registers. You are writing to it. Okay, let's say I write a 1 here. Okay, we write a 1 here. What does it mean? It actually means, okay, let's say if this one is for port 2. Okay, and since I write 1, I'm writing 1 to the false bit. So basically, I'm setting P, let's use 0, P0.4. I'm actually using this pin to indicate to trigger the interrupt. So whatever device connected to this pin is an interrupt device. Okay, and since you are using ENR, R here means rising edge. Just like your push button, right? Your push button, if I draw your push button signal, if no one is pressing it, it will be 1. Right? Remember, it's active low. Whenever people press it, you will get this, right? And if you release it, you will get this, right? So your push button signal will be like this. Okay? So you see, you will create a negative pulse. So you want this one to be your interrupt signal, means whenever you sense a button press, you want to trigger something immediately. Just like when student knock the door, I should answer the question immediately. Okay? So the action knocking the door or coming to my office, that's a trigger event. Okay? So here, the button press is a trigger event. And it will trigger some other event, like I'm answering questions. Or this one will trigger, let's say you turn on the light, let's say. Okay? So for this, you see, you can either use this edge or this edge to trigger something. Okay, so can you see, this is a falling edge, this one is a rising edge. Okay, so you can either you can either sense here or sense here to sense the button press. Okay, so ENR, this register, if you put 1 here, means I actually want to use the rising edge to trace something. I try to keep monitoring, is there any rising edge? Okay? If you want to use falling edge, you should use this register, ENF, falling edge. If you write 1 here, okay, so basically you are using the falling edge. Okay, so this is the usage of these two registers. Again, they are write-only registers, means we define, right? We are defining whether we want to use this or this. So you are writing 1 to this register or this register. Okay? Then this is just a setup. Basically, after you write 1 here, you get your system ready. Okay? You are telling your processor, okay, you should sense the rising edge or the falling edge. Okay? But how to know that whether there is actually a button press? You need to sense the button press. Okay, how do you know this one occurs? How do you know this your processor is already sensed the falling edge or rising edge? Is by looking at these registers. So these two are telling you the status of your interrupt. So you are basically reading it. Okay? So we need to keep looking at here or here, depending on you are writing here or here, okay? Let's say I use this one, I use a falling edge. You did this setup, then you keep monitoring here, okay? Originally, it is 0, okay? But once you realize that this bit becomes 1, okay, your processor will change this one automatically, okay? But we need to write our own program to keep looking at here, okay? Once you sense a 1 here, you know that there is a button press. Okay, so this is the way we detect the interrupt. Okay, so basically here you need to read here. Okay, and once you realize here becomes 1, so there's an if loop, right? If this one is 1, you write your code like turn on the light or play the music, right? The event that you want to trigger by this interrupt, right? But after you finish your task, after you turn on the light or after you play the song based on the button press, what do you need to do? You need to clear here and here. Okay, you need to clear both of these so that your system is ready to sense the second time of your button press. That's why you need this register interrupt clear. Again, here is a write register. We need to write purposely here 1 once we finish our light turning on code. Once you write 1 here, your ARM processor will clear this bit and this bit. Okay, see the flow? So this is how you sense the GPIO interrupt. So go back to our question. You have 2 push buttons here and here. So if I'm using this figure, okay, it tells you, okay, let me see my question. P2.0 and P2.4, right? So you can imagine that, let me change another color. So here is my port 0, okay, so this side will be my port 2. So I have one P2.0, I can imagine here is connecting to one of the push buttons. Okay, and I have another one as, for example, here, okay, let's say here is P2.4. I can say here is another push button here. Okay? But they are all using GPIO interrupt. And they all be treated as ENT3 interrupt for NVIC. Okay? Whenever here and here are pressed, NVIC will sense an ENT3 interrupt. Okay? So what you need to do is, in your main program, okay, in your main program, you need to enable your GPIO or ENT3 interrupt. This one needs to be enabled. By default, it is not, right? You all have, for those who have your lab already, you didn't do anything for interrupt, right? You just do regular routine. Your program is keep sensing the buttons in the main function. Okay, so it's not the interrupt. So if you want to use interrupt, you need to enable the interrupt first. Okay, then as I mentioned here, you have many pins for GPIO. You have also a specific pin for ENT3. So here you need to declare the corresponding pins for GPIO interrupt using rising or falling edge. You need to tell that, okay, which pin or pins are actually connected to your interrupt device. And you also need to declare whether you want to use the rising edge or the falling edge. Okay, so these are kind of settings. Okay, so you need to have this before the actual program start to run. Okay, so these are the setup. So I write it here, setup. And once you set it up, if you did this correctly, we don't need to write any code to sense your SW3, your push buttons. For those who have done your lab, remember in the lab how we sense the push button? We do btn1 equals to GPIO read value. We read from port 2, right? And then we write shift 10 times. We end with another value. We wrote this code by ourselves in our while one. Remember, in our while one infinite loop, we keep sensing this again, and again. So this is we call regular routine because you wrote the program. Whatever you write in the while one is regular routine. It's keep running. Okay, but for this case, it's an interrupt. Once you have done this setting, your processor is automatically trying to capture the signal from the pin. You don't need to write any code to sense the pin by yourself. Okay? Because you see this one is actually, let's say, okay, as I say, this one is in the while one. Right? In the while one. And in the while one, this is not the only code. You have some other code. And then you finish your while one. So basically, your while one will run this line all the way to here and then repeat all the way here, right? Imagine you have 1,000 lines. Okay? Imagine, let's say, each line take 1 second to execute. That's it. Okay? So see, this one will be first second you will do this. Second time you will do the next line. Then the third second you will do the next line. If you finish one round, it will take 1,000 seconds, right? Which means if let's say you press the button at the first second, you can capture it. But let's say once I press, I release, and I try to press the second time at let's say 500 seconds. Are you able to capture it? You cannot, because you are in the middle of somewhere here. And the code is not sensing the port. Okay? So in the middle, if you are running something else and you press the button, it will not get captured. Until the next moment, if you are lucky enough, you just press it. At this moment, your button is get pressed. Either you are holding it or not. You are holding it for 1,000 seconds, you will capture, it will get captured again. So this is a disadvantage of regular routine. It's highly depending on the length of your code. Okay, how fast you can sense your switch, your push button, depending on how long your program is in the while one, right? Let's say your while one can finish very fast. 1 second you finish everything, means you are able to sense your push button every 1 second. But if this part is very long, 1 hour, let's say, means the sensitivity of your push button is 1 hour. You know, to sense the next one, you need to hold for 1 hour and then it get captured. So this is the disadvantage of regular routine. So interrupt is different. As I said, if you have done this, you don't need to write any code here. And while you are running something for your regular routine, your processor is sensing the push button by itself automatically. So whenever the button is pressed, no matter where you are, no matter which lines you are, it will get captured immediately. Okay? So that's the difference between regular routine and interrupt. So once you have done this, you wrote this in your main program, you don't need this line anymore. Okay, you don't need this one anymore. ARM is keep monitoring your button by itself. And once it gets captured, as I said, you don't need to sense this anymore. Okay, but how to know that the interrupt happened is once your arm senses the push button, it will automatically jump to the interrupt handler. Okay, so this is like a function, but it's called not by us. Okay, you see, this is the way we call the function, right? We need to write our code here. So when your program is executing this line, it jumps into this function. But handler, you can imagine this is a function that only your ARM processor can call. Okay, we are not able to call it by ourselves. So your ARM processor will call this function and jump into this function once your ARM processor detects the interrupt. Okay, so you can construct your following actions inside this interrupt handler. That's why here you identify the peripheral that caused the ENT3 interrupt. Why do we need to do that? Because the interrupt, okay, so whatever gets sensed from ENT3 by your NVIC, no matter what device is this, it will call the same interrupt handler. It will call the same interrupt handler, same function. Okay, that's why inside the function, the first thing you need to know is identify which device caused this interrupt. Because many devices can let your arm jump into that handler. Okay, so this is the first thing you need to identify. Okay, once you identify that, you can do your action. You can say turn on the light or answer student questions. Those are your following actions, right? You can construct the code inside the handler, or you can define an indicator. Let's say a flag. I raise a flag. Okay, then later on in your main program, you can have a flag. You can have a flag checking to do the action. So I will talk about this later. And after your follow-up actions, you need to clear the interrupt. So that next time, if you don't clear, can you see? If you don't clear, you will keep jumping into this function. You will keep jumping into this. You cannot exit from this. Okay, so that's the idea. Then how to write the code? As I mentioned, in the main function, you need to do the setup. Firstly, these two lines. Can you see that this is INT, E, and F? I'm using falling edge. Okay, port 2, pin 0. Because remember we have two devices are at port 2, pin 0 and port 2, pin 4, right? So basically these two lines is to tell the processor that, okay, these two you should take the signal as interrupt. Whatever signal coming from these two pins, they are interrupt. And you should sense the falling edge of it. Okay? So this is these two lines. And this one is to enable your ENT3. As I said, this is shared by your GPIO. So there's no GPIO IRQN. There's only this one. So for GPIO devices, you also need to enable this. So this is a function in the library. If you are curious, you can open your code and see what's happening in this function. But this is a function used to enable your interrupt interface. Okay, so these are the two actions you need to do in the main program. Once you have done that, you see I don't have any code to sense my buttons. So then you have, okay, maybe you have other programs after that. You have your 101, but they are all talking about other devices. You don't need to write any code for these two push buttons. So your ARM processor will automatically run something here and sense this by itself. Once it realizes some buttons here are pressed, you will automatically go here. Can you see that? ENT3 IRQ handler. So when any button is pressed, you will automatically jump into here, your code. Okay? So you are going to execute this. After this, it will go back to the main function, and if you didn't clear your interrupt, it will jump into this again. Get the idea? So here, once you jump into this, first issue, as I said, you need to identify which device is caused you to jump into here. So you have if loop. How to detect which device is an interrupt? You see, you sense the status register. Okay, so this is status register. Remember, they are read-only registers telling you whether the interrupt happens or not. Okay, so you have this if loop. If IO2 interrupts static F, right shift 0 times, same as your lab. Okay, right shift 0 times, you bitwise AND with 1, you will get 1 if this bit is 1. You will get the whole thing 0 if this bit is 0. Right? So if this is true, you know that the device connected to your P2.0 is trigger this event. Right? Else if I check the other pin, so P2.4. Okay? So either this or this, depending on the question, I should print the same message. Right? Button pressed, button pressed. These are basically the follow-up actions. Right? And then you need to clear the interrupt. Remember? So to clear it, you go to the clear register, set the corresponding position of the bit to 1. You write 1 to the clear register. You need to do this inside this 2 if loop. Okay? If you don't write here, you will keep jumping into this. Okay? So get the idea? So this is the idea of the interrupt. Okay? We will talk about this in detail in the lab in week, I think, 9. Okay, week 9. Two weeks later.
现在是 week 7
Okay?
week 7这个礼拜，明天没有来吧？
So this ends this tutorial.
Week 7.
Any questions? So here, if you don't quite understand the code, doesn't matter. Just I hope you get a rough idea the difference between the interrupt and the regular routine. Okay? Okay, that's all for today. Thanks.